Good morning to everyone. Last video we have discussed about the derivative of stiffness matrix and then global assembling of global stiffness matrix for an one-dimensional element. In this video we can going to discuss about the real-time problems. Springs are assembled in a collinear as shown in figure. The node 1 and node 4 are fixed. If the axial loads are 20 kN and 40 kN applied at nodes 2 and 3 respectively. Determine the element stiffness matrix, global stiffness matrix, displacement at node 2 and 3, reaction force at node 1 and 4. The figures are shown in below. In this, they are having a 3 springs. Spring 1 stiffness value will be 1500 kN per meter. Spring 2 stiffness value will be 2000 kN per meter. Spring 3 stiffness value will be 2500 kN per meter. And then the axial force acting at node 2 will be 20 kN and node 3 will be 40 kN. The node 1 and node 4 are fixed. So first we want to find the element equation. So K1 equal to 1 minus 1 minus 1 1. For element 1, K value will be 1500. So 1500 minus 1500 minus 1500 1500. This is the stiffness matrix for K1. And then K2 stiffness matrix will be 1 minus 1 minus 1 1. The stiffness value of element 2 will be 2000. So 2000 minus 2000 minus 2000 2000. And then K3, the stiffness value of element 3 will be 2500. So the matrix will be 2000 minus 2500, 2500, 2500. Here we are assembling an element S. For element 1, the node 1 and node 2 will be influencing. For element 2, node 2 and node 3, and then element 3 will be node 3 and node 4. So for element 1, F1, F2, stiffness matrix of U1, U2. For element 2, F2, F3, stiffness matrix of U2, U3. For element 3, F3, F4, displacement of U3, U4. Now we are going to assemble the stiffness matrix. So if we assemble the stiffness matrix, that totally they are having a 4 nodes. So stiffness matrix size will be an 4 cross 4. So 1500 minus 1500, 0, 0, minus 1500, 1500 plus 2000, minus 2000, 0. Next 0 minus 2000, 2000 plus 2500, minus 2500. Next 0, 0, minus 2500, 2500. So final matrix will be 1500 minus 1500, 0, 0, minus 1500, 3500, minus 2000, 0, 0 minus 2000, 4500, minus 2500, 0, 0, minus 2500, 2500. Now we are applying a boundary conditions. For node 1 and node 4 will be 0. So if the displacements will be constrained, the corresponding row and column can be able to eliminate. So node 1 and node 4 will be 0. So first row, first column, and then fourth row, fourth column will be eliminated since because of fixing displacements. So remaining value 3500 minus 2000 minus 2000 4500 U2 U3 equal to 2040. Solving these two equations, the U2 value will be 0.00144 meter. U3 value will be 0.015 meter. So displacement of U2 will be 0.0144 for node 2. Displacement of node 3 will be 0.015 meter. Now we are going to find the reaction force. So stiffness matrix 1500 minus 1500 0 0 minus 1500 3500 minus 2000 0 0 minus 2000 4500 minus 2500 0 0 minus 2500 2500. So U1 value will be 0, U2 0.0144, U3 0.0155, U4 0 into F1 value 0, 40, 20, 0. So finally we find the reaction force is equal to for node 1 minus 21.69 kilonewton and then node 4 will be an minus 37.5 kilonewton. Thank you.